This is another touch detection circuit similar to the one in Project 1, except now we're using a different configuration that allows for more sensitivity, so we can get much more brightness out of the LED without putting any more current through your hands. So this is what the original brightness was. You can see how much brighter it is with this configuration where the first transistor is controlling the base of the second one, so you get more gain. The AI version of this circuit also made just a standard Darlington pair. The only difference was it added a 10K resistor to the collector of the first transistor, I'd assume just for extra protection, so there's not too much current flowing into the base of the second one, but it functions just the same. Here's an alternative touch circuit generated by AI. It is using a 555 timer. In the internal comparator circuit, it's not very sensitive, but it does fully turn on the LED whenever these wires are connected through touch. It does need a very close touch though, and a firm contact of both wires, unlike the other touch circuits which required barely any contact at all. This is the instantaneous switching circuit. It's just a basic BJT switching circuit that uses a switch. The switch in the diagram is normally closed. I only had one that was normally open, so it just does the opposite behavior, where this would be the default, and then that would be pressing it. So you can see that the LED responds immediately to the change, unlike some of the following circuits which have delays and fades. This transistor circuit uses an LED and an LDR to create a latch, so that whenever some event, like a light flashes in this case, it will save that until the light is blocked from in between those two, and then turns back off. This is a relaxation oscillator circuit created using two NPN BJTs. I cannot find any rhyme or reason as to how the LEDs turn on. Certain transistors work, some don't. So I think there's some variability there. This isn't really a circuit that is designed with the proper usage of a transistor in mind. It's making use of the breakdown behavior on reverse bias. And like I said, half the time it works, half the time it doesn't. And just getting two of these working took a very long time because I just had to kind of randomly select components until it worked. To get an even better idea about the variability of this circuit, even changing out a single LED, for instance, with a different color can stop it working at all. And then as soon as I reinstall the white LED, it will flash. I have not found an answer as to why this happens. I guess the different colors have some different characteristic. I can't really locate any in particular that would make sense for that to be the cause. This is the AI generated relaxation oscillator circuit. It, as you can see, does not work. I'm not entirely sure why. It generated something very different than anything I could find online. I'm still having trouble getting it to draw pictures, so I think maybe next lab I'll try a different AI. But the circuit did not work. It's basically just a diode across the collector and the base, and then the capacitor is to the base as well. So it's supposed to charge up until it reaches a point where it discharges across the diode, but it's not working. This is the first LED fade out circuit. It just has a capacitor across the base, so that stores charge when it's turned on, and then whenever it turns off, it keeps the VBE high enough to keep the LED on until it's fully discharged, in which case the transistor turns off and the LED no longer has any power. This is the second LED fade circuit. It uses a capacitor across the base to, whenever VCC is enabled, it slowly charges up until it reaches VB on. So this gives it a slow turn on behavior. But then as soon as the VCC is disabled, it will return to its off condition because the capacitor does not store more than VB on, so there's not enough voltage left in the circuit to turn the LED on. The circuit fades in and then back out as power is applied. Once the capacitor charges high enough, it turns back off, but it takes a little while to charge, and during that the current is going through the LED. This is the fourth fade circuit. It is a fade out circuit, so when power is applied, the LED turns on fairly instantaneously, and then whenever power is released, it takes a while to turn off. Power is stored in the capacitor and just keeps outputting through the LED until it's discharged. This is the AI generated fade out circuit. It did not work. I think it is doing the same thing as one of the examples where it's only charging the capacitor to VB on, which is not enough to sustain the LED after power is removed. But how it's configured, it's also not providing a fade when the LED is turned on either. So it did not function. I think it's a matter of the AI does not know how to choose the right resistor values for this specific purpose. It tends to kind of generalize things instead of selecting components for a specific use.